About the motivation, I'm sure a lot of you already wouldn't be here if there weren't a lot of interest in the Metro platform. But from a games perspective, which is kind of the most common use of DirectX in today, it's a really good fit for the Metro platform because, for example, all applications on Metro platform have many features that games typically have had for a long time, such as, for example, coming up in full screen by default, and having that immersive experience. Also, the store makes it really easy for you to create experiences that you can be very creative with, as in traditional methods wouldn't have been able to get those out to as many customers as you can today. The other opportunity is that we're now taking the existing hundreds of millions of PC users and then growing that in terms of people, in terms of eyeball minutes and opportunity, out to include newer sets of devices like tablet PCs. And then the single APIs that we're providing as part of the Windows runtime span all of those devices, so you can use the same application to cover a much broader audience. The focused API set is easier for people to learn, and many of the APIs that we're going to be talking about today, game developers are already familiar with because they've been using them already in C++ for classic apps. And then, of course, the other advantage of getting started now is you get visibility. One of the toughest things when you're starting out as a developer is getting attention for your product. And so the sooner you get out there, the fewer other applications will be competing for mind share. Okay, and this is our obligatory slide showing the spectrum of devices. These ones on the left side of the screen are the ones that are creating the newest opportunity for people to create. And so our focus in all of our Metro applications, and especially games, is to encourage people to use touch and other new input modalities like, say, accelerometer to really exploit the portability of those devices that are coming on the left-hand side. Okay, so now that I've talked about the platform a little bit, the opportunity a little bit, we'll talk about the platform, then we'll step through some of the steps of creating a DirectX C++ application in the Metro context. So we'll go through the initialization sequence, how to get a window, doing some 3D graphics maybe, a little bit of mention of policies and practices around these things, including file I/O, how to do some more different types of input, and then sound effects and audio. So this is the slide that you guys are all familiar with. I want to call your attention to the unique orange square that we pasted in there just for you, which is kind of where the DirectX API set comes in. You can call the DirectX APIs directly from C++ and not necessarily have to use XAML at all, although you can also create applications that use DirectX for some things and XAML for other things like, say, UI layout. The ability to call it through C# DirectX is a little bit challenging. You have to really use third-party components like that was just mentioned, SharpDX and SlimDX. And then there's not really a good story for going in through HTML directly to to DirectX, because really DirectX is down there in that blue box called Windows Kernel Services, really, and some of the lower level components that are plumbed through. So HTML is already using DirectX, but technically I believe if you wanted to call, say, some of the direct compute APIs, you could do that from inside a JavaScript app using the WinRT projection model that was just discussed. It's really tough to get bits on the screen from DirectX up into a JavaScript application. So getting into a little more detail, this diagram, we've got this low-level component, which is really the Windows runtime that does input and then has things like display for DirectX. And then on top of that, you've got a bunch of options for how to create applications. And so for the HTML scenario, there's this component called the Windows Web App Host, which lets you create your applications in JavaScript HTML. That's fine. That all works. It used to be called Trident internally. Or your other option is to use the XAML framework and the Windows runtime components there and build an application using that UI toolkit, for example, in C++ or C#. But if you don't want to use that, if you want to write effectively your own framework, we have this other component called Core Window, which is an analog of those other frameworks, except it's kind of the non-framework framework, or it's the framework that you use if you're going to write your own framework. So an application that wants to write their own custom engine, like a game engine, for example, will call just the low-level Core Window APIs and then write their actual application code on top of that engine. Right? So what we're going to be talking about today is a lot about Core Window and the iframework view interfaces that connect to the operating system from a C++ application with very, very minimal intervening layers. So the iFramework view is really the class that you implement if you want to be a pure C++, frameworkless app. The 5 methods on this interface are basically the methods that the operating system uses to call your application and invoke it explicitly. And then there's this concept of a core window, which is analogous somewhat to an HWind in that it provides input mechanisms, input events. Instead of the message pump, there's separate callbacks. And then there's also the service that it provides in terms of telling you where your pixels go when they end up on the screen. So how you get a window, how you get a view, what happens to that window with the input events. Okay, so we're going to go through first the app activation process, which is based on this iFramework view class object. It's, like I said, there's only these five methods. The first is an initialization step, which basically the application is telling you that, hey, you're now going to be started up. The set window call is when you get notified about the actual core window object that you will be using to display your content in. The load method is called immediately after that, and then run is called, and then when you're terminated, often you'll get an uninitialized call, but not always. So, it's pretty straightforward. There's a whole sequence of recommended best practices for this that we'd like to cover in this slide, for example. So what we'd like people to not do, for example, is load all of their assets in the load method and do so with synchronous load calls, right? That's probably the worst case scenario. What you really want to do is as little as possible in these early methods, and then so that you can get your application up and running and do it the right way. So what happens is at the very beginning, when the user clicks on, say, your live tile or some other way to invoke your application, the operating system has pulled out of your package the splash screen. And it puts that splash screen up on the screen. Like you can see here, it's Marble Maze is centered in the window there. It doesn't get stretched. And that is displayed. And then your application binaries are loaded into memory. As in, your application is actually loaded at that point. Once it's loaded, the OS calls the load method, where what you need to do then is ideally asynchronously, but it shouldn't really matter because you want to load the absolute minimal amount of data that you can initially, which is just enough to bring up a loading screen that you'll use later. So you load the assets for the loading screen. So this large Marble Maze sign in the middle is something that you would load up at that point. Hopefully it's one fairly small JPEG file, and then whatever assets you need, like background music, to play during the little animation of your actual asset loading. Then what happens is when you return from that method, the OS will call you the run API on you, which is really where you put all your application effectively inside that method. And the first thing you do there is actually load real assets, meaning the meshes for a level or all the sprites for your characters or whatever it is. Things that will take a significant amount of time that you want to give the user a progress bar about how long that's taking. Because then you can animate things inside the run method, which we'll see a little bit later. And then once your app is actually completed loading enough assets to be able to start playing, that's when you switch to this menu screen and say, okay, I'm ready to start playing, and then offer the user the option to start. And then once they hit start, then you go into the gameplay. But that's all done inside the run method of the actual iFramework view application model. So let's take a little more detailed look at some of the events that we get in from input from the core window. Once we've got one of those assigned to us from the OS, we can get some events on it. Now, the way a lot of this works is this is our recommended best practice for how you implement that run application, where you, in the run method, get the opportunity to specify when your events are sent to you. So you create this dispatcher object off of the core window, and that is actually the mechanism that fires all of the callbacks for the events that have happened since the last time it was called. And if you use this process all if present option, when you actually call the process events, that guarantees that all of your input events that have been queued up till that point in time get executed by your own handler code. And then after that, you know that you can call an update of your own internal application state that the assumption is this loop is running at 60 frames a second for an animated application. You would update all the state that needs to change based on the inputs that were received by the handlers in the process event call. And then once you've got your, all your characters in the right places now, you can render, which means you call all the graphics APIs and create an image that's containing all those characters or so on. And then when that render is complete, you've got an image you can call present, which is another, there's actually a DirectX low-level API underneath that takes your final completed image, puts it on the screen, and then it actually synchronizes that presentation of the image with the vertical monitor vertical refresh rate, so that you don't get cases where you're seeing half of one frame and half of the frame before. And the other thing that does is it effectively throttles the execution of this event to running of this loop to running at 60 frames a second. And so that means that, for example, if you've got a really simple scene on a high-powered system, you're not rendering at 2,000 frames a second and melting the battery because the user can only still see 60 frames a second because that's how fast monitors refresh. So that's the nice thing about that present method. The one thing I want to point out here is this process all if present. There are a variety of flag options for the process events call that provide different behaviors. Another variant of that is one that causes the application to wait after every set of inputs and wait for the next event. And in that, if you're doing something like a Mahjong or a Solitaire or Minesweeper, maybe that's the type of application you're working on. But if we're doing something like, say, an arcade game like Pong or something where we're assuming that by default almost everything is animating all the time and there's no point in just blocking anywhere, then you use this option. Okay, the other interesting aspect you get from Core Window is this concept of view states. We've got sort of the 4x3 version, we've got the 16:9 version, we've got the, you can see there on the left-hand side is the snapped view it's called. These are all different view states that your application can be put into. And then of course there's the portrait orientation as well. So these are all view states, and you'll get a notification into the, through an event on your core window called window size changed. And this is the opportunity in the handler for that event for you to lay out your content because like in this case, we're not using XAML. There's nobody going to do automated layout. You would need to do things like potentially reallocate some memory resources if they are tiled memory, for example, or just position things like the scores and so on around the screen. There are plenty of options. Like there are third-party toolkits, like for example, Scaleform, that are UI toolkits written entirely in Direct3D that you could use at this point as well. And we're not doing anything in this piece of dummy code here, but again, this is where you look at the bounds that come in as properties of the event, and depending on whether you've been rotated to a new orientation or whether you've been snapped to a smaller vertical mode or filled to full screen, those bounds will come in as the corresponding size of that region that you now own on the screen. And so you can relay out your assets. With DirectX APIs, you have access to individual pixels kind of by default. So it's not the standard resolution independent model that you get from the other frameworks. Now about rotation, while you do want to handle your rotation events in that same callback, you have some say as an application on the types of orientations that your application will be rotated into by the OS. So for example, if you say, okay, I don't have a preference or rotation, which is the default at the top, my orientation will be whatever the OS tells me it to be. I'm basically saying I can handle anything. And then if the user takes my tablet and rotates it to whatever angle, I'm still going to work. If I'd say, okay, I'd really like to only work in landscape orientations and not portrait orientations at all, I can just make this call like at the bottom where it restricts me to just a subset of the preference orientations that I'd like to have. And for example, if you set only one of those, say just landscape, then you are effectively locking your application to only ever be at landscape orientation, for example. The interesting thing is you can set this parameter either in code like this or in the manifest itself, which will then govern the behavior of your layout screen, of your splash screens during launch, even before your application has been started. Now, on the best practices for this, our encouragement is that applications should try to support as many different orientations as they can, like ideally all four. If you've got an event-based game like Solitaire or Mahjong, there's just no reason to not let the user rotate it however they like while they're playing. If you've got a real-time game like, say, Asteroids, where there are rocks coming in trying to hit your ship all the time, the rotation, when the player rotates the screen, they might say, okay, I'd rather play in this orientation for a while. You could let them do that, but you have to keep in mind that there's going to be an animation that occurs. So what we recommend that people do is when you get the event saying, okay, I'm being switched to a different size, that you suspend or pause the gameplay at that point and then resume it with a timer so that it gives time for the animation to end and it gives time for the user to get back their thumbs on the right joysticks before the gameplay starts up again. That gives them a chance to not get hit by a rock during the rotation, for example. And then, of course, even in those types of games, if the user has paused the screen, say they're in the settings menu or they're between levels, then yeah, go ahead and allow rotation. And then, of course, a lot of non-real-time, your average app is also going to be something that really should support all orientations. The exception where you do want to lock rotation, for example, is a game like Marble Maze that we'll be showing later today, which is an accelerometer-based application. So if you're using the accelerometer to steer something on the screen, you can't have it also be rotating your application simultaneously. So that's one of the cases that you really want to apply the lock scenario. Other than that, it really should be a goal to try to get your application to run on as many different orientations as possible. And then wanted to point out here for those of you who are doing things on, say, focus change, there is an equivalent to that also as part of the core window. It's called activation change, and there's a couple different states that you can look at here. You can find out when you've been deactivated, when you've reactivated, as in when the user has given focus back to your application, because there could still be two applications on the screen. One of them could have focus and the other one not. The whole concept of focus still is important in the Metro environment. And when you regain focus, there's a potential that it could have been done through a code mechanism or from the actual user input, like a click from the mouse. So that distinction is also available to you in the API. Okay, so now we're going to start to get into some of the more game-specific technologies. This is really the whole list of technologies that we believe are relevant to game developers that are part of the Metro API platform. There's a set for graphics and then for cutscene playback and so on, input mechanisms, audio. Then there's a variety of different network and services and tools. And I'm mostly going to talk today about the Direct3D graphics output, some of the pointer input mechanisms, and then some of the other input mechanisms, and then a little bit on Xaudio too, just a slide or two, just to point out that there is a games API that you can call from Direct3D for audio. So on graphics, this is the first thing that we want to make very clear, which is that the core graphics API is Direct3D, and it's really we selected that because it was the most popular graphics game API, at least out there right now. If you look at probably the total number of installations and the total number of users, it's probably the most popular graphics API. And the version that we selected, we had 3 versions, 9, 10, 11. We selected the API to be the 11 syntax. So what that means is anybody who's got existing DirectX 11 code, it should just work in your application, except for like the one entry point you need to change to call to connect to a core window. DirectX 10 code, if you've got any of that, Direct3D 10 code, it should also be very easy to port to DX11 because the fundamental architecture of those APIs is extremely similar. DirectX 9 code's a little bit trickier to port, but if you've still got your 9 shaders, you should be still okay. But this topic of versions is potentially a little bit confusing because while the only API version that is supported in the Metro platform is version 11, version 11 operates in a couple different modes called feature levels, several different modes anyway, and those correspond to other versions of hardware. So you can have an 11 API that runs on 11 hardware, but you can also have an 11 API that's running on 10 hardware or 9 hardware. And in those cases, the API restricts the feature set to what is supported for that generation of hardware. So you'll get development time feedback on whether you're trying to do something that exceeds the capability of that generation of silicon. So for example, on a DX11 chip, like probably the majority of systems out there today are DX11. You get the full suite of features. If you're on a DX10, you get slightly fewer features. If you're on DX9, you get this baseline functionality for the platform. So the way you manage this in the API is you specify at the time you create your interface to Direct3D, basically the Direct3D device object, what the feature levels are that your application is able to support. So you can specify from this enum, or this is actually a list, you can specify the entries from that enum in the list, and that tells the operating system what are the ranges of feature levels that you have specific, potentially optimized code paths for each of those, right? And then we recommend that lower left, the bottom flag there as well for best practices. But then what happens is you take this list and you pass it in as to the creation of the API interface effectively, the list of feature levels that your application can handle. Now what will happen is when you create the device, it will come back and try to get you the highest value on that list that device can support. So if I'm on an 11, I've asked for a DX11. If I'm on an 11 card, I'll get 11 as the feature level that I've got, and I can use that. It means that I can now use DX11 code paths throughout my application. And then this is where the feature level comes back from the implementation. If you're on a DX9 chip, for example, the highest feature level supported will be DX9, and you'll know that because that'll be the one that you get back, and you can use that flag to select the 9 code paths in your application, or the 9 optimizations. And so the only tricky bit is if, for example, you run on a piece of silicon that only has its maximum level lower than the lowest level that you specified, then this call will fail. And in that case, you need to put up a dialog box saying, this application doesn't support that feature level hardware. A couple tricks here is if you really want to play with this, an easy way to do it initially at least is instead of buying 3 different types of graphics cards, you can select the feature level that you like in the DirectX control panel, dxcpl.exe. You can find that with search. And then the implementation will restrict itself to the behaviors of whatever level you pick. So if you want to run on DX9 cards, but you happen to have a DX11 card in your machine, which is kind of what we recommend, so you can do a test run by setting this, and then it will allow you to validate your code paths for that scenario. Okay, so now this is the one API call that's unique to the Metro environment in that it creates a DirectX object called the swap chain, which is really the output of the Direct3D renderer always goes to a swap chain. You can create that swap chain out of a core window. So when you got initialized with set window, you have a window now. You can pass that in as the window that you'd like it to build a swap chain for. And this is what fundamentally connects Direct3D to the Metro environment through the core window object. Okay, now when I actually do want to start rendering, this is a snippet of code from some of our samples. This is the way the rendering call would be implemented there. When you're ready, all your data is in the right place, all your objects are in the right place. You've got some information that you want to convey to the screen. You need to make a set render target call here, which is really how you guarantee that swap chain is really what the D3D device is targeting that every frame. You have to, since we're asynchronous, we have some loading complete checks in there to guarantee that the assets are actually ready to be rendered, because you don't want to try and render anything before you've loaded it. But once you have, then there's these ideas of vertex buffers and index buffers and textures and so on that represent the content that's going to appear on the screen. And then You can actually set the shaders, which are the snippets of GPU code that gets executed in HLSL to shade the objects that are presented on the screen. And then you call draw, and your data ends up on the screen. So this is all in the samples, the DirectX samples. I'll give you a list of those in the last slide. Now, one of the other aspects of graphics is it's important. I mean, the main reason that people are using DirectX and C++ is because they want the low-level access to the hardware that gives them the performance and also, therefore, power efficiency. And so tuning for performance is kind of the goal here. And so we want to make sure that people understand how to do that. There are a variety of different options that you can control in how you use the API that you can use to scale your application performance across, say trade-off image quality versus performance across a broader range of hardware. So you can have everything from a lightweight tablet all the way up to a dual SLI gaming rig. And so these parameters that we've got right here are the ones that are easiest to adjust. So there's a filter called anisotropic filter quality that affects performance, and it varies also a little bit the image quality that results. Low values of that mean slightly less image quality, but they also mean higher performance. Another easy to tune parameter is, for example, anti-aliasing. You can set 4x or 8x MSAA, it's called, at the very high end, but just use 1x at the low end, and you haven't had to make any significant changes in your code to scale for performance. Other than that, say that one parameter. Another common trick to adjust performance is to actually render your image to an off-screen buffer that is smaller than the actual final screen, and then when you go and present it, it gets stretched up. It can be stretched up to the full pixel size, and then typically you'll put your scores and so on. Things that really need really high detail will be put on that way, and that's a common technique used in a lot of games today. And we have a sample. I believe our resource load, our post-processing effects sample does that technique today. And then also, what may happen is that if you really need to vary the way your application performs between a very high-end system and a very low-end system, you may have to actually provide lower poly count versions of some of your assets. Hopefully, those other techniques help more. For example, if we're talking about image quality, it's also possible to scale your image detail by modifying how many levels of the art assets are provided. Typically in a 3D application or any type of application that you want to have able to scale dynamically with, say, screen resolution, you'll create a lot of your assets in this format called a mipmap, which stores half-size versions of every level of the multiple copies of the image, each scaled down by half all the way up. And then what happens is the hardware can just pick the corresponding one that's closest to the current magnification that it needs. And it does this in a fairly sophisticated way that results in pretty high image quality. But what it means is that you have this ability to adjust performance by selecting the maximum level of detail that you want your applications to your application to use on that particular piece of hardware. So if I don't think that I have enough performance to allow a 1K by 1K texture, I'll just set the MIP level clamp to 512. In fact, our asset loading samples will just clamp that limit to some value that you can specify so that they don't even have to pay for the memory cost of loading levels that you're not going to use. But this is kind of an example of the image difference in quality. I mean, the gameplay would still be there. It just means that on a less powerful device, then I would probably have less detail, say, in the sand on the bottom than I do on my higher-end device. Another example optimization that we encourage people to look at is the fact that also for targeting these newer devices, a lot of them support a reduced precision arithmetic mode, which is faster, in some cases 2 or 3 times faster than the default. So the way you handle this is instead of using floats in a lot of your, say, GPU code, you use this concept of a min float, which basically says, I'm okay with this float actually being done at 16 bits instead of 32-bit precision. And that allows, for example, a lot of these implementations to execute twice as many of those per clock, which saves power and improves performance. But the output argument is always still full float, so that it remains interoperable with every other shader in the system. Okay, so our recommendation for managing this type of hardware environment is to, if you're going to be using DirectX, go ahead and get a recent machine, use a DirectX 11 based system, and be sure to have the opportunity to exploit the full features of that system, but start out with your lower level features and then build up. If you're starting with a new code base, you can build up by starting with a DX9 level of image quality and then add more features for your DX10 and 11 code paths. And as far as performance goes, it's very important to be able to adjust with those techniques I just listed, the image quality versus performance trade-off, so that you maximize the experience you can deliver even on a low-power device, which may not even have a fan. And then, of course, manage this feature level difference. And now as I said, there's a dialog box that lets you pick the feature level that you would like your existing system to emulate. That lets you restrict it down to a lower level, but there is also a mechanism that will let you, say I've got a DirectX 10 development machine, I want to target a DX11 system, I can either go buy a DX11 card for it, or I can turn on our software emulation called Warp, which will deliver the full 11 or 11.1 feature set, but the trick is that won't be at the same necessary performance that a dedicated hardware chip could have delivered. But it's enough to validate whether your code paths are actually functioning correctly. And then eventually, once you've got to the point of really wanting to release on these different types of hardware, try it on a couple different machines. Try it on a tablet, try it on a netbook, a notebook, or a desktop. Okay, I want to put a little bit of info on how you save game state, just because this is different in the Metro scenario. The APIs that you call, we've just been talking a lot about today for asynchronous persistence in various different ways. But the interaction with those is interesting because of the process lifetime manager. There's a possibility that your application is going to be suspended, which means put in this kind of intermediate state between terminated and running, where it's still present in the operating system, but it's just not consuming any clock cycles. So, and then once it's in that state, you don't know necessarily whether from there it's going to be resumed, in which case it just starts getting clock cycles again, or whether it's going to be terminated because the OS needed all of the resources that application had. So to be able to make your application work well, you want to conceal all of this from the user. You want to make them believe that your application never was terminated and is always suspended, or is actually even always running in the background. So what that means from a game perspective is that it's important to save state frequently, so that if the application is terminated, when it comes back, the state will be where the user left it, and they won't be able to tell the difference between whether they just got suspended and resumed, or whether they got terminated and restarted. So a lot of games today dump out all of memory into a save file when the user says, okay, I want to save at this point, and they go through this long process. And that's really annoying to a user, to make them watch that progress bar while the hard drive light spins and so on. It's not a very immersive experience. So there's a lot of advantage to breaking your save operations up into smaller pieces that can be performed at a more frequent interval that hopefully the user doesn't notice. Now, if some of those start to take up some time, that's why you want to schedule them for potentially breaks in the game experience, like say at the end of a level, or when the user's updating a menu, or when they pause for some other reason. That's a good time to write out any large amounts of state that would be the kind of thing that would be noticeable to the user, and of course, do all that asynchronously. Then what you can do is, ideally, at every frame, or even at very fine intervals like that, every few seconds, you can update a small amount of state that is incremental to the larger chunk that was persisted. So it really depends on the type of application, how you want to manage this. But the thing we're really asking people to do is to focus on delivering a more streamlined experience around file I/O than we've seen today on the desktop. And then one of the other points is that if you're coming back in the middle of gameplay from a paused state, and it's like, say you switched out, you've got a chat message or an email, you go work on that, you swipe back to your game. If it's something where there were asteroid headed towards your ship, be nice and let the user resume gameplay off of a counter or something, instead of just having those asteroids suddenly hit before the user has really finished realizing that they're back in their game. Okay, input's important for a game because if there's no input, it's kind of just a movie. So the way this is the most common type of input is from the core window object, where you've got these event handlers that you can register for. They get called back. They get executed by the operating system, but they do so at the time you call them through when you call process events. The default mechanism for, say, input is this concept of pointer point, really, or the pointer APIs. And these are agnostic as to whether they come from a mouse, a finger, or a stylus. So touch, mouse, and stylus are all unified into the single event model that Core Window exposes to your application. And so by default, if you just ignore lower levels of detail, you'll get consistent behavior in your application between all three of those devices. Now, it is also possible to look at the event that you got and look at some of the data that came with it and discern whether that object that sent that event was a mouse, a finger, or a stylus. But by default, at least, it means you'll get consistent behavior. In this case, the data that comes back with the event includes, for the case of a mouse down or a pointer pressed, you get your position, and you also get an ID. The interesting thing is that now we've got multi-touch devices where effectively it's like having 10 mouse cursors or 10 input mechanisms all present at once. It's important that your application be able to distinguish which input event came from which of those 10 fingers. And so this concept of pointer ID is provided by the operating system that will actually track to some degree fairly well which finger it is, even across multiple frames. As in, pointer ID will not change very often if it's the same sort of finger that's moving around generating events. As far as input goes, a lot of games just pull for keyboard state. They don't even necessarily use events for that. You can use events, but this is an example of polling for state. A lot of our samples do that. And it just means that as you're going through that loop 60 frames a second, every one of those ticks you're checking to see whether there's a key down or not, asynchronously. Now, the other new input device as part of the Metro platform is this concept of sensors. And the cool thing about those is you can expect that a lot of these devices will have an accelerometer. Accelerometer is pretty common. In fact, the new devices not only have an accelerometer for linear dimensions, they have accelerometers that detect rotation as well. And so those have a basic pass-through API, and you can call those to find out the g-forces through the accelerometer and the angular accelerations that come from the gyro. And there's also, I believe, an API to check the compass that comes from the 3D magnetometer. But also in the implementation, we have created a setup where the OS and some of the drivers take all three of those yellow boxes there and integrate the data together into a single parameter, which you can query, that is effectively the current orientation of the device. So if you look at this last box on the bottom right, that is a fusion of information from acceleration, orientation from the gyro, and then orientation from the compass. That is, all of those values are synthesized together to produce a single current orientation value, which tells you effectively how your device is oriented in space. Not all of our devices have this today, but it's something we support in the operating system, and therefore, over time, more hardware will be shipping that supports these capabilities. But fundamentally, this value comes back from this object called an orientation sensor, and you just get the reading out of it, and it comes back as a thing called a quaternion, which is basically a 4-vector describing an orientation. You can think of it as a direction for an axis of rotation, and then an angle about that, then with some trig applied. And then, for example, we're using this in a math library that creates a transformation matrix at the bottom here, and then we can draw an object oriented using that transformation matrix, and so therefore it appears like it can stay in place in space, even though I'm rotating the device that I've got all these sensors in. So it's a very simple mechanism, and it's something that we encourage people to use when they're creating accelerometer-based applications. Okay, the other interesting thing is that the platform for input not only includes mouse and keyboard, accelerometers and sensors and so on, it also includes, and touch, it also includes joystick-style game controller inputs. And this is accomplished using a Win32 API, which is not part of the Windows runtime, but it is wrappable. We have seen people wrap WinRT wrappers onto it to call it from the other languages. I believe the controller sketch sample that shows how to do this includes that kind of a wrapper so that it can be exposed to JavaScript. But this is the fundamental C++ code. It's the same C++ code that you would use today on a PC or on an Xbox to determine the inputs coming in from that kind of controller. So we're encouraging people to support as many different input mechanisms as they can. In the past there were policies that would say, don't have multiple ways to do the same thing. Well, some people are going to have a device that's only got touch on it, so they can't use a mouse and keyboard. Some people are going to have a device that maybe only has a mouse and keyboard and not touch. And some may have, some controllers may be present or not. So the ideal thing from our recommendation is to support as many of these different inputs as possible, and that way your users can use your product no matter where they are, right, in the broadest range of possible scenarios. Okay. On the other side, there was some talk about this already, this concept of game audio. And really what this amounts to is that there are a variety of services in the operating system, even exposed into the Metro platform for managing audio. The sort of default one, obviously, is the one that plays back MP3 and other types of music and even video clips. And that's really not that suitable for games because it's assuming latency, because those APIs are designed to make sure that plays very smoothly and glitch-free, but not at a particular millisecond in time. So another option is there's a low-level API called Wasapi, which, Windows Audio System API, very, very low level, extremely fine-grained control over exactly when audio sounds happen. It's used by a lot of these voice telephony applications, for example. But the issue there is that it's not able to support multiple different sound effects happening at the same time, right? In a game, you're likely to have, a sound track in the background that's music. You'll have some explosions. You'll have, people talking. All of those need to be blended together simultaneously, and the Wasapi API doesn't provide that capability. So the Xaudio 2 API is really something that, again, has been used on other devices like the PC and the console for a while to deliver this type of game-specific audio, which means, yes, it's got low latency, and yes, it supports mixing a variety of different streams. So that's a very similar model to any of the DirectX APIs. You create this interface to the API through called the mastering voice. You open up your data file. I don't think that's any of this is asynchronous, but it should be. You create an actual, you effectively are converting your data file data into the runtime format that the API will play back. And then when you call the playback, you start the audio for that sound at that point in time by playing the buffer. Okay, so I'm going to talk a little bit about adding Metro-style features. These are important because, well, we want people to basically exploit the full functionality of the Metro platform. For example, the philosophy here is, again, to convey to the user the concept that their applications are always there. They don't need to worry about, like, is it running yet? Is it not running? Is it suspended? Is it resuming? The objective from the end user experience is that it's always there. And one of the ways to encourage that belief is to have a live tile, it's called, which is if I've got my application and maybe if it's not running, I go to the start menu, I can still see a live tile that may be animated at some relatively sane frequency. that helps me believe that my application is still there. So in the game scenario, for example, you could have that update the user with the state that they're at. Like say if it's a simple game, it could just be what level they've achieved at that point in time, like say the jumping jacks has done. Or there may be more dynamic information like who else that I know is already playing that game, and maybe I can get back in if enough people are there, or how long until I've got some meeting set up where I'm going to meet these people in the game and we'll all play together. So there's a lot of APIs or a lot of documentation on the APIs for setting this up. It's not really anything specific to the games about how to make it work. We're just talking about what are some of the examples of best practices that you could use these APIs for when you're in a game scenario. For example, there's my notification where my live tile has updated me with the fact that, hey, I've got 3 other people that I could be playing with right now. An equivalent or an analogous capability is this concept of notifications. And these are for events that are even more urgent, where it's actually going to be worth having the user see this on top of anything else they are doing. So the challenge there is to make it something that they would care about enough to not mind having that happen, because if they are annoyed by it, then they'll turn off notifications from your application and then you won't be able to tell them anything. So it's a little bit of a balance trick there. So examples would be, if I've got some multiplayer game running and some other player has logged in and started to attack my base, then that'd be a pretty interesting thing to notify the user about. If a friend has just logged in and they want me to play right now, then that might be something that you would give them an immediate notification on. And again, there's a variety of templates and APIs and documentation on how to set these up as well. The interesting thing about both this and the live tiles is that Microsoft provides a server that lets you broadcast this information out to all of your users from a single point that we can offer if you want. But there's an example of a notification that's interrupting me when I'm playing PowerPoint here. So that's what this is just a reminder to what those look like once they're really going. And we'll have some demos. Well, I'll talk about this one first. Another common user interface paradigm in Metro applications is this concept of an app bar. And so I know that many applications will already have their own menus and so on, layout about where to keep things like settings menus and so on. But our objective is to make it so that if users have a muscle memory around where they get settings for different applications, and it's all the same, then they have a much easier time running the whole platform. So the app bar is typically this bar that comes up at the bottom of the screen. It's brought in with a gesture that's a swipe up from the bottom of the screen. In many cases, if you've got, say, like I said, an asteroid scenario, you'll probably want to pause the game when that app bar is up, because the user wants to go change some setting and they don't want to die while they're changing a setting. And then there's a simple API that you can use even from C++. I mean, normally this app bar is handled by your framework. So if you're in XAML, you'll get, you can just basically list the things that you want to have in your app bar, and it pretty much does everything for you. In the DirectX case, when I'm just using C++ and core window, I need to directly go in and write code that hooks to the raw events that come from the operating system when this app bar gesture is first triggered. And the nice thing about that is I get 2 events. One when the gesture has first been detected by the operating system, and then one when it's completed, which is basically when the user's thumb has come up off the screen. And that lets me present my own app bar. Potentially maybe it's done using an art style that's unique to my game because I'm rendering it myself in DirectX code. But at least the mechanism that the user goes to bring it up is consistent with everything else. In an analogous sense, there's also this concept of a standard settings pane. A lot of games and other applications have a settings menu, and by having them all being brought up using the same input mechanism helps users discover them. They know that without even having to look on the screen, without having to have a special settings button on your application. You don't need to have that because users will usually always look for that with the swipe in from the right, and And if you've got a settings pane, then that's where you should put it, because that's where the users expect it. So by default, all the OS provided settings are there as well, but you can add your own set of settings that are specific to your applications that will come out at the top of the list. And you can even vary that list of options based on the current state within your application. Like if there are settings that don't matter because the player hasn't gotten to that level yet, then you don't need to list them, for example. So in this also we have a C++ API set that lets you get access to this at a low level, so you can implement your own version of a settings pane, which again could be done using DirectX 3D calls in your own visual style that's unique to the game, but still be invoked using the same input mechanisms that guarantees that the user's muscle memory will still apply to your application. And so in this case, we show how to add a couple different. We add a new setting to that list called difficulty, and then the difficulty is the first one is our list of commands that we're adding this to. Then we append an entry to that list, and the difficulty at the top is the token that is used to identify it from our API. And then the set difficulty string below that is the string that actually appears on the settings menu. In many cases, you're just going to enter one of these saying, my settings, and then maybe you'll bring up your own more sophisticated settings dialog off of that. Okay, and this is where I like to bring up Matt to have him demonstrate these Metro-style commands in the context of a game. And the point I want to make about this is that by adding these types of Metro integration to your application, it makes it look like it's a complete app. It makes it look like it's a professionally written app, not just some freeware, shareware thing. And so this is important if you want to get paid to implement these types of completions in your products.
Okay. Yeah.
So how do you switch?
Oh, it's gonna go on. All right. So this is the Metro-style Marble Maze game sample. It's actually available on MSDN right now, and you can go download it. We made some slight modifications to illustrate some of the features that Chaz just mentioned that'll really make your Metro-style games light up on the platform. So this is a simple game. You get the marble to the end of the maze, and you win. So there's a timer, and which appears to be cut off. But in any case, so there's so let's say I'm playing this game, and let's say I'm not very good here. So I keep falling in the holes. But let's say I actually know that there's this settings menu that will enable me to actually cheat at the game. So I'm going to go bring up the settings bar here and click enable cheating. There's an enable cheating option at the top here. So I'm going to click that. Oops. So one more time here. Enable cheating, and then I can press the cheat key to go straight to the end of the maze and cheat to get a high score of 26 seconds, which I think beats my real best score by about 5 seconds. So let's say I want to actually brag to Chaz about this. I know he'll never believe me, so I actually want to send a mail directly from the game. So what I can actually do is I can invoke the share charm here, and we see that the application wants to share my high score, so I can select the mail app, which will consume this text in this case. And here we have, I just got a new high score in Marble Maze, 26.3 seconds. So I can send this mail to Chaz. And I don't think he'll believe me, but you see I can send the mail directly from the app. I don't even need to leave the app because of the share charm here. Oops. And now we can go back to the start screen. And if we actually look at the tile here, you can see that it will update with an example of some high scores. Now these are hard-coded in the text here, but what you can actually do is you can imagine updating these dynamically based on, say, total high scores, a high score server system. And if you actually notice in the top right here, I don't know if it'll be cut off, but there'll be a notification that you can see that'll actually show. So yeah, unfortunately, it's off the screen right there. But essentially, a pop-up has popped up that says you've been banned for cheating. So you could imagine this type of notification coming down from the Windows notification system that would inform the user of a critical event like this, even when they're not running the game. So again, this sample is available on MSDN. It's using the Xbox controller, so you can pick up a USB receiver for this for about 20 bucks if you already have a controller. And so now I'll hand it back to Chaz.
Thanks, Matt. Okay, can I get my microphone back? It sounds like I have it. Okay, thanks a lot, Matt, for that quick demo of the extra polish that a Metro app really needs. So again, the best practice here is go ahead and adopt these features in your application. It's good for your application because the users really like to hear about your app, or it's better for you if your users hear about your application more often. So if you have a live tile that's updating, every time they go to the start menu, they can see actual useful information about it. That's positive. But in addition, like I said, it makes your application look professional and therefore something that people will be willing to actually pay money for in the store. Our objectives are to make the UI guidelines consistent around how these features are invoked so that users can learn a very common way of doing what they need to get done. But again, in a lot of cases, you can extend the visuals there to support more artistic viewpoints than just, say, the square rectangles that a lot of our UIs are looking at default right now. Okay, one of the other things I wanted to mention here is that I wanted to basically thank the developer division for creating a Visual Studio product this release that has a bunch of explicit support for the DirectX C++ scenario. So the first one, of course, is they've actually brought C++ up to the current standard and even augmented it with C++ CX. All of our application samples that are provided in the SDK right now on the website are written using the new HAT syntax, the C++ CX, just because we thought it was cool, and we deal with a lot of COM objects in DirectX, and being able to manage those was very helpful. Then, of course, they've done work to implement specific file new project templates for two different kinds of DirectX applications, a two-dimensional one that's sort of an event-based model, and then a three-dimensional one that is the real-time run loop like I showed today. They've also gone to the trouble of incorporating Direct3D HLSL for GPUs directly into the environment so that you can get syntax highlighting, you can hit F5 and it compiles it and inserts it into the package for you at the time the package is actually being built, along with any other DirectX assets that you may have in your project. And then you can even actually, not beyond just package those, you can actually look at them in many cases by just double-clicking on them inside the IDE, because they've added support for things like textures and in some cases meshes into the product. Especially in the Pro version, you can actually double-click on a 3D mesh that you've added to your project like any other file, and then it will bring it up in a 3D view and let you look at that mesh to make sure that it's actually correct, for example, when you're developing your content. So thanks, guys. And then, of course, they've also done some improvements to the way we've integrated debugging tools into the Visual Studio that let you potentially step through code that's graphics code, identify potentially what's happening in terms of the GPU state that may or may not be correct, is causing some artifacts. You can even do things like select a pixel on the screen that looks wrong and then have the debugger effectively tell you all of the API calls that might have affected that pixel, and you can go step through that list and see which ones look suspicious. And then you can even potentially step through shader code. Do we step through shader code? Yeah. So you can actually, debug code that's running on the GPU using that IDE. So it's been a huge amount of work they've done, and we in the DirectX team really appreciate that. Okay, so there's a couple little hints I threw on the end of this slide, but really we're pretty much done with this talk. I'd like the search thing on the search text port in the IDE is really nice for these types of commands. Also, a recommendation is to do things like set up a dual mon config. Have your touch monitor on your left as your main primary, and you can run all your Metro apps there, and then you have your IDE and your debugging environment on the secondary monitor. That makes a really nice, fast development environment because you can just switch back and forth with Alt-Tab. Then as a hint to where put a breakpoint to catch some of the exceptions that we throw for our error messages in the DirectX APIs. And then this is really my final summary slide, which is, the time is now to get out there and get started. If you see these samples and you look for them in the search pane of the Metro App developer site, you'll be able to see all the source code snippets that I showed today and be able to do pretty much anything in DirectX with the Metro application. So thanks a lot. Thanks, Matt. And it's good to be here. Okay, we'll take 3 questions, he says.
3 questions? Anybody have a question? Yes, we have a question.
3 wishes.
Is it possible inside of your own application in Metro to handle right-click differently or block right-click so that the app bar does not come up?
Yes. Because you can register for that handler yourself, the code that you put in it is up to you. And so, again, our objective is that if you've got something that looks like an app bar, it should probably be enabled to be brought up with something like a right-click. But if you don't, or if you have some other scenario that really, really needs a right mouse click, then you don't have to bring up an app bar there. There's a set of recommendations in some of the game-specific guideline docs on exactly that issue, but that's really the summary. Am I right?
When you said you can debug the GPU state, or you can actually view the GPU state, the GPU will be paused for that time, or GPU will be running and it is a running state?
It actually is really only debugging the copy of the state that we retained on the CPU. So it's the CPU's idea of what the state was at that point when that, say, frame was generated or when that pixel was generated on the screen. It's not actually freezing the GPU's execution. It's all done through mirroring information on the CPU.
Yeah, and what about the pixel? You said about the pixel, you can select the individual pixel for, so we have the control over each and every pixel. We can see what operations have gone on the pixel.
Yeah, again, it does that when you're in a debug mode where it effectively creates a log of the API calls that were used to generate the image, and then we query that database. It's kind of more like time travel than really interrupting the GPU and actually querying its state.
All right, one more. Where can you find the documentation for pretty much everything that you mentioned? For instance, the offline compilation, everything in Visual Studio 11.
The documentation for that?
Yeah.
Well, I thought it was in the Visual Studio documentation. It may not be. We know the docs may not be complete on that specific topic. I know they're in progress and we're working on them. It's just a question. I don't know what's hit the web today versus the next couple weeks. Yeah. But the thing to do for sure is to look at for offline compilation the resource loading sample. It's called DirectX resource loading, and that contains a project that actually has build rules in the MS build environment that do the offline compilation not only of shaders, which is built into the IDE, but also of meshes and textures that then get built into your package. It's very similar to what XNA does.
One more question.
Okay.
Is there anything different in developing DirectX applications for ARM than for other platforms?
Well, our goal on the ARM is to make it as similar as possible, right? To make the platform consistent across all the processor architectures like x64 and x86 as well. The main difference I think that you'd run into initially is that the range of graphics feature levels is different. On the ARM devices, they tend to be more DX9, 91, 93. On the x86, they tend to be more DX9, 10, 11. Right, so that's that's not necessarily tied to either platform. It's just the way the market looks today. It's not there's no hard rule there.
Well, let's take one more question.
Just for fun. This is what's great about live.
What input APIs are available for additional input devices such as joysticks? Xinput just supports Xbox.
Yeah, it supports Xbox compatible controllers, which means if you go buy an Xbox compatible fishing rod controller or steering wheel or baseball bat or whatever they sell. Those will all work, even joysticks and so on. The question is whether, how we get support for even third-party tools beyond those.
Basically, what's
is-
the direct input replacement? What lets me get, buffered or raw input state and pull for state and get it in a nice struct rather than an event-based system, and will let me do so for arbitrary devices from third parties.
This is sort of an evolution of DirectX. It's just X input, and it's not really event-based. You do pull for state. You don't get raw
Well, X
data.
input is, but for other devices,
Yeah.
non-Xbox compatible.
We don't have a good story for that right now in this initial version. There are mechanisms where OEMs can potentially, or device vendors can hook up specific applications to their device, but there's no mechanism where an arbitrary hardware vendor can create an arbitrary model of a device and provide it to all applications in the Metro platform today.
Related,
can
are there
silent-
plans to have more of like a raw touch input layer?
Yeah, but
Similar to maybe the XNA one where it just populated a struct with data?
Charles, you guys can sideline if you want, because you're going to go
Right.
back and forth a little bit. You can sideline if you want, so we can let Jesse. You'll be in the back, and you'll be taking Q&A later,
Yeah.
right?
Yep, I'll be around, so it's time to end the questions.
Go ahead and
and we'll
sideline
to
with
Jesse now.
Charles. Yep. All right. Let's get Jesse ready.